Okay, today we're going to start looking at the Doppler effect and its effect on light and redshift in galaxies. So let's review quickly the Doppler effect. So we know if, say you were standing at the side of the road and an ambulance drives past very fast and it's beeping, you hear that as the ambulance approaches and then as it passes you and then goes away from you, you hear the frequency of the siren change, and this is caused by the Doppler effect. So let's see, you're here and our ambulance is here. I'll do a kind of ambulance cross thingy, a wee light, and what we see is as a velocity of, so we've got our ambulance in this direction, some velocity, and it's emitting light waves. So let's draw circles to represent the light waves. The change in frequency that you hear, the apparent change in frequency, that's what frequency is a result of compression or elongation of the effective distance between the waveforms, or the wavefronts, sorry. So this is emitted, and as this moves out, the ambulance is moving in that direction towards the wavefronts. So it's going to have the effect of this wavefront's going to appear to be closer to that than the natural wave of light would be if it was the ambulance was stationary. But the opposite is true here, as it's moving away. Is the wavefront from this wavefront to the one previous is going to appear to be stretched, elongated. So in this part here there's a compression and here there's an elongation. So if we draw another wavefront, you've got that compression and that elongation. I'm making it quite exaggerated. We'll do one more. They're not meant to be touching. It's meant to be uniform, but you get the idea. So what has happened, let's change the colour here. So we've got our wave coming out of the ambulance. I'm going to change the colour, that didn't change. So we've got our wave coming out of the ambulance. And as this ambulance is moving towards it, the wavefronts kind of get squished together. So you can see that it'll affect the pitch of the wave as it comes towards you. But as if you imagine like a slinky being pulled, the ambulance is pulling away. Those wavefronts are getting pulled out, elongated out, so the wavelength is bigger. Now the wavelength, sorry, is the distance between two peaks or two troughs. That's your wavelength. And our observer is here. So when we talk about our redshift, we'll talk about the source as the emitter, and we'll talk about in this case, the wee person listening as the receiver or detector. The equation for the observed frequency, so the frequency that the person here will hear, is equal to the source frequency, so the frequency at source, the emitter, multiplied by the velocity, so that's the velocity of the source, divided by the velocity of the source plus or minus the velocity of the, so the velocity of the source, that's the velocity of the wave. So this is the velocity of the wave, and this is the velocity of source. So what we can see from just looking at this equation, so sound waves are moving at fair speed, not as obviously as fast as light, but they're going at a fair speed. So if, say, you were walking towards somebody and talking, your velocity is going to be significantly less than velocity of sound. So there's going to be no Doppler effect on that. So it's when the Doppler effect becomes more evident the closer the velocity of the source is to the velocity of the wave. So the velocity of the wave and the source are both in meters per second. Nope. Didn't put my bracket in the right place. Meters per second. And the frequency is in hertz. And this is the observed frequency and the source frequency. Sorry, that frequency. Now, the plus and the minus. So, the plus and the minus must be selected for the relative motion of the emitter towards, or away from. So, if it's negative, if the emitter is going towards, and positive if emitter is going away. So back to our ambulance. And this, if you wanted to find out what the frequency of the wave was, the observed frequency for the person here, you would use minus. But I say you had another person, I'm going to draw this person with a little skirt on so that we can. So we've got a wee girl over here. She's got, for her observed frequency, you would use the plus, because they're both going to have different, they're going to observe different frequencies. Now, this is for sound, so the Doppler effect here is for sound, but it also is seen in sound and light. So we can see the Doppler effect happening in light as well as sound. Now, quickly let's look at stars for as going to be our light source. So we're thinking about the Doppler effect in stars or galaxies. Now, stars and galaxies are moving relative to one another at high velocities, and therefore we can actually observe the Doppler effect on light. Now let's just explain something about light coming from stars. So this is our sun. If we analyze the light coming out of it, and you see all the different colours, so you'll have like blues, yellows, and reds. So if you were to break up the frequency with a spectrometry, you would be able to break up the white light from the sun into its constituent wavelengths. And what happened is, when this was first done, a German physicist called Fraunhofer in 1814, he analysed the light from the sun, and he found 500 missing wavelengths. So when the sun is generating the light, the light, so here's our surface of our sun, the light is coming out and it has to pass through an atmosphere. And this atmosphere is made up of different gases. And light, when light passes through gases, certain wavelengths are absorbed and emitted. And so what Fraunhofer was seeing, as the light was passing through the outer atmosphere of the sun, there was the different gases that make up the atmosphere would absorb certain wavelengths, and this has now become a way of analysing the composition of stars, because these wavelengths are like a fingerprint for different gases. So different gases will absorb very specific wavelengths of light, and these 500 missing wavelengths that Fraunhofer found became known as the Fraunhofer Lines. And so we can see them here. This is the wavelength, and these black lines here are where the gases in the sun's atmosphere have absorbed certain wavelengths, and these chemical fingerprints can be observed in other stars. But what physicists discovered was when they started to look at stars and the starlight coming from distant stars and galaxies, they actually just found that the lines, the Fraunhofer lines, were not in the correct places. They were either shifted a little bit to the right or a little bit to the left. And they're redshifted. This is an effect of the Doppler effect. So if this is the Earth, it's a terrible Earth, and this is some distant star over here, and say that star, so we're moving, our Earth is moving around the sun, and the sun is the solar system is also moving around the galaxy really, really fast. But our whole galaxy is moving through space at mind-boggling speeds. But if you were to look at a distant star or a distant galaxy, that star or galaxy will be moving relative to Earth. If you think about the previous lesson, we talked about frames of reference, and the frame of reference that the Earth is moving in relative to this frame of reference. So say this star is moving in this direction away, so it's moving away at some velocity, some high velocity. The light is redshifted. Now say we've got another one over here, another star over here, but this time, relative to each other, this star is moving towards us with a different velocity. This is going to be blue shifted. Now how it works, the principle is exactly the same as the Doppler effect when we looked at the ambulance and the different sound. It's just that we're now dealing with light. Now in reality, there's far more stars that are redshifted than blue shifted, and we'll be looking at more about that in the next lesson. So we can measure redshift, and the degree of redshift is given by this equation Z, where Z is the redshift. It doesn't have any units. So Z is equal to the wavelength observed minus the wavelength at rest over the wavelength at rest. Now, with redshift and blue shift, we deal with wavelengths, not frequencies, and that's more just a convenience thing. When we're talking about, we're dealing with cosmology and in astrophysics, we talk about the wavelengths of the light from stars, not the frequencies. So that's why when we were talking about the Doppler effect with sound, we talked about the frequency, but with redshift, we'll deal with wavelengths. The wavelength is measured in meters. Now, if Z is positive, this means we've got redshift, i.e. the star is moving away. Likewise, a negative Z will be blue shift. Now, note this. For stars and galaxies, relativity would need to be considered, but not in this course. The maths of that it gets quite complicated, so this is not going to be discussed in this course. So we're just going to be dealing with non-relativistic velocities. So for non-relativistic velocities, Z is equal to V over C, where C is the speed of light and V is the velocity of the star or galaxy. Now, starlight analysis is really is a significant part of astrophysics. It can give you the chemical signatures of stars and galaxies. It can help you determine the degree of redshift. So redshift or blue shift will tell you what direction a star or galaxy is moving in, and the speed of such a move relative to our own velocity. And it has been a driving force of 20th century astrophysics and cosmology, and has yielded some very significant results. What the next one some of them will be looking at in the next lesson. So I hope that helps.